So we have to see how we can use these master bounds, since by themselves they're not anything that can be immediately used. So one of the examples that we saw last time was with matrix Gaussian series or Rademacher series. So this works as follows. Let's suppose that our matrix Y is a sum of gamma k times ak, where ak are fixed, deterministic, in other words, and known ahead of time matrices, and the gamma k are IID standard Gaussian random variables. So as we saw last time, we had the following result. When the AK are d by d Hermitian matrices, and if we let sigma squared be defined as the norm of expected value of y squared, which a simple check, basically by independence of by assumed independence of the gamma k, this equals the sum of ak squared. Then the expected value of the largest eigenvalue of y is bounded by the square root of 2 sigma squared log d. D again is the dimension. And we have a tail inequality, the probability that the largest eigenvalue of y exceeds t is bounded by d times e to the minus t squared over 2 sigma squared for all non-negative t. And the proof of this was quite straightforward. Again, we had to plug into the formula we had above. So step 1 is already done for us. We already have y expressed as a sum of random matrices. So these are our xk. Step 2 is to compute the moment generating function of the xk. And we did this. And we did this last time, and sort of straightforward computation shows that this is e to the theta squared a k squared over 2. And so this is the whole point, that computing the MGF of this is doable in this case, whereas computing the MGF directly of y is much more difficult, and we can't appeal to this to writing the MGF of y as a product of the MGFs of the individual ones. That's the whole point of our master bounds and of using Lieb's theorem. And then we plug into our master bounds from before. We solve the optimization over theta, and the result follows. After this, again, we did this last time. We moved to another application of our master bounds, and we gave a matrix Chernoff bounds. In this case, when xk are random, independent, and in addition, the new assumption is that they're positive semi-definite matrices. So the assumptions we need are that each xk is positive semi-definite. Recall that that's what this is the ordering with respect to the semi-definite cone. So just a brief reminder, this is equivalent to writing that a minus b is positive semi-definite. And the additional assumption we need is that with probability 1, the largest eigenvalue of the xk is bounded by some parameter r. So now let's let y be the sum of the xk, and let's define the parameters mu max to be the largest eigenvalue of the expected value of y, and mu min to be the smallest eigenvalue of, again, the expected value of y. So then the theorem says that under this setting, the expected value of lambda max of y, okay, so note that this is the expected value of lambda max. Mu max is the lambda max of the expected value, is less than or equal to e to the theta minus 1 over theta times mu max plus 1 over theta r log d. D is the dimension. We also have bounds on the expectation of the smallest eigenvalue of y. This is greater than or equal to 1 minus e to the minus theta over theta times mu min minus 1 over theta r log d. And we also have tail inequalities. So the probability that the largest eigenvalue of y exceeds a multiple of 1 plus delta times mu max, this is less than or equal to d times e to the delta divided by 1 plus delta raised to the 1 plus delta. All of this raised to the mu max divided by r. And this is true for any delta greater than 0. And we also have bounds on lambda min of y being less than 1 minus delta of mu min. This is less than or equal to delta times e to the minus delta over 1 minus delta raised to the 1 minus delta. All of this raised to the mu min over r. And this holds for delta in 0, 1, including 0, not including 1. So these proofs need something different in our formula, in our recipe. And the reason that they need something different is that we have to ask ourselves, what do we want the primitives? What should the primitives be? Now, in the previous example, we could compute this quantity. This quantity was rather simple. But in this case, the primitives are in some sense the random variables. The random variables xk are basically all there is to the problem. It would be very difficult to come up with these general bounds. So what we really want to do is control this term in terms of what's given in the problem, which is essentially expected value of xk. So we need expected value of xk in order to compute mu max, and so we'd like to control it in terms of these. So for this purpose, we need a key lemma. We need the following lemma. If X is a positive semi-definite random matrix with its largest eigenvalue, always bounded by R with probability 1, this is exactly our setting, then the following holds. Then the expected value of e to the theta x, this is a matrix, so it's less than it comes before in the semi-definite ordering another matrix, and that matrix is e to the r theta minus 1 over r, that's a scalar, times the expected value of x. And from that we can quickly get that the log of expected value of e to the theta x is again less than, in the ordering, e to the r theta minus 1 over r times expected value of x. So what's happening here is that this is the matrix that appears in our master bounds. But instead, we will use this one. So one key point is the fact that trace respects the semi-definite ordering. So that's one of the key facts that we're going to use and why this is useful. So let me just rewrite this to be clear here. This is the semi-definite ordering. These are matrices here. That's what this lemma shows. So I'm not going to reprove this here because we proved this in class. But just remember that the proof comes from is very simple, and it's based on ideas of convexity. And the definition of convexity, that basically says that if you have a convex function, then any point on the chord lies above any point on the function. So that's all it comes from. If you don't have the proof in your notes, you can just try showing it. It's quite straightforward. So now let's put this all together. So for notational convenience, let me just find g of theta to be this quantity e to the r theta minus 1 divided by r. So what do the master bounds tell us? So the master bounds tell us that expected value of lambda max of y is less than or equal to the inf over all positive theta 1 over theta log trace exp sum over k of log expected value e to the theta xk. So you see this is where we have this log expected value of e to the theta xk, and because of the monotonicity of trace exp, we can replace that with what's on the right hand side by the lemma. So basically, but the lemma tells us that this in turn is less than or equal to. Note that these inequalities this is now the usual ordering for real numbers. So this is less than or equal to the infimum 1 over theta log trace exp g of theta times the sum of expected value of xk. So I've just basically used the lemma and then the linearity of expectation to pass the summation. To pull g of theta out. Sorry, just the linearity of summation there. Okay, so what happens now? Now we're going to use some of our standard tricks. We have this. Write it a bit more clearly. We have a trace here. So a standard bound is for trace is to replace it by the dimension of the matrix times its largest eigenvalue. So this is certainly less than or equal to the infimum of log, and instead of trace now, d times lambda max of whatever's inside. Exp of g of theta sum of expected value of xk. Now another standard thing that we've seen and follows immediately from the definition of exponential is that we can now pass lambda max inside. So this is now equal to inf 1 over theta log d exponential of lambda max g of theta sum of expected value of xk. Let's go to the next page. So just copying. So we had that expected value of lambda max of y is less than or equal to the infimum over positive theta of 1 over theta log d times exp of lambda max of g of theta sum of expected value of xk, which is exactly expected value of y. And lambda max is of course a homogeneous function, so g of theta can come outside, and that basically concludes the bound that we want. So this concludes the proof of one of the 4 points of Matrix Chernoff, but the others follow more or less in a similar way. So let's now give an application of Matrix Chernoff. Let's suppose we have a matrix that looks like this. It has many columns, and I'll call the ith column, or the kth column, bk. So it has d rows and n columns, where n is bigger than d. And let's let bk be the kth column of b. So that means that we can write b as equal to the sum of bk, the column vector, times the outer product with ek, where ek is the standard basis vector in Rn. In other words, the vector that has zeros everywhere and a 1 in the kth position. So what we might want to understand, and this relates to randomized linear algebra, which we talked about a few classes ago, is what is the behavior in terms of the spectrum, in terms of the largest and smallest singular values of a subsampled matrix. So let's let Z be a subsampled matrix, and I'm going to write this as follows. Essentially copying this expression for what B is, let me write Z as exactly the same sum, except I'll multiply each one by a Bernoulli random variable. So where a to k is Bernoulli with probability s over n, so that therefore on average Z will have just s non-zero columns. So I basically zeroed out some of the columns. So the question that we ask is, what are the largest and smallest? How can we control these singular values of Z? Again, I want to use Matrix Chernoff. So it takes a step or two to get this question into Matrix Chernoff. For Matrix Chernoff, we need to write things, our random matrix, as a sum of independent positive semi-definite random matrices. And Z is not even positive semi-definite itself. So that's not what we want to look at. So instead, let's look at Y equal to ZZ transpose. So now Y is a random matrix. And this will tell us what we want, since the largest eigenvalue of Y is equal to the largest singular value of Z squared, and the smallest eigenvalue of Y is equal to the smallest singular value of Z squared. And moreover, I can now write Y as a sum of random independent positive semi-definite matrices. And basically just by computation we can see how to do this. So Y is equal to ZZ transpose. Looking at the definition of Z, we get that this is equal to the sum over indices j and k, a to j times a to k times bj ej transpose times ek bk transpose, and this is equal to the sum of a to k times bk bk transpose. And I've used the fact that a to k squared is equal to a to k because eta is just a Bernoulli random variable. And indeed, this is a sum of positive semi-definite matrices because each of these is a rank 1 positive semi-definite matrix. So this is step 1 in our recipe. We need to write the quantity that we want to understand. We need to write that as a sum of random matrices. Step 2, we need to compute the quantities or bounds on the quantities that appear in our bounds. In this case, in the Matrix Chernoff theorem. So, in other words, we need to compute mu max. And mu max, recall, is the largest eigenvalue of the expected value of y. And this is straightforward to compute. So, expected value of y, by linearity of expectation, it's the sum of the expected value of a to k times bk transpose. Expected value of a to k is just the probability that it's equal to 1, that's s over n, times the sum of bk transpose, but this is just B transpose. In other words, mu max is equal to S over n times sigma 1 of B squared, and mu min is equal to S over n times sigma D B squared. Now plugging into Matrix Chernoff and setting theta equal to 1, we get that the expected value of sigma 1 of z squared is equal to the expected value of lambda max of y, which is what we want to control, and this is less than or equal to e minus 1 let me write it more clearly, e minus 1 times s over n times sigma 1 of b squared, the largest singular value of b squared, plus r log d, and the expected value of the smallest singular value of z squared. This is just equal to the expected value of lambda min of y, and this is greater than or equal to 1 minus e to the minus 1 times s over n times sigma d of b squared minus r log d. So one of the applications of this is to give guarantees on when a subsample of a matrix will be non-singular. So some other applications that are quite similar. One is we can think about subsampling rows and columns. So this is basically saying if I give you a fixed matrix and I randomly select a submatrix of it, what are going to be its extreme singular values? So the question is about the extreme singular values of a random submatrix. Another question, which is explored in the homework, is an application to random graphs. An application to Erdős-Rényi random graphs, where we want to where the question is compute conditions to guarantee that a GNP is connected with high probability.